So, before moving on, let me resume what we were talking about in the previous lesson about the BB84 QKD protocol. We can sketch the protocol in 6 steps, followed by Alice and Bob. First, Alice encodes a sequence of bits in randomly selecting a basis, horizontal, vertical, or diagonal, anti-diagonal, and randomly selecting the bits, 1 or 0. She sends them to Bob. Second, Bob receives those photons and selects randomly his basis in order to measure them. Third, Bob communicates with Alice over a public channel. A telephone line would just work fine. He tells Alice his choice of basis. Fourth, Alice checks Bob's choices of basis and tells Bob to discard those bits where they didn't agree on the basis. This can be done also over a public channel. They both discard those bits, and they end up with a shifted data bits. Fifth, Bob transmits to Alice over a public channel a subset of the shifted data string he measured. And sixth, Alice performs an error analysis. If there is a 25% of error, they discard the shifted key as not secure. If error is less than 25%, she deduces that the key is secure and she sends the encrypted message to Bob. Now, but the real world is not perfect, and there are some things that can go wrong and introduce error to the key, even without if. Let's talk a bit about error correction then. Even though you have all your quantum channel controlled and optimized, you can have photon deletion. It could happen that a photon is lost and doesn't reach Bob's detector. The medium, be it air or optical fiber, is going to absorb photons because some of them will interact with atoms in the medium. Those photons will be lost from the data string. It can also happen that the photon reaches Bob, but Bob's system is not perfectly aligned and it doesn't make it to the sensor of the detector. It could also happen that the photon does reach Bob's detector, but the detector doesn't click. If this is the case, we will say that the efficiency is not 100%, which no detector is. Typical values for efficiencies are around 80%. Some can reach 95%, but they tend to require temperatures of 4 Kelvin. All of this, of course, will affect the key that Alice and Bob can generate, but this won't leak information to Eve. This will shorten even more the shifted key that they will generate, but for this, there is nothing that Alice and Bob need to do about. When Bob shares with Alice which basis he chose, he will do that based on the photons that he actually detected. The non-detected ones don't count. Alice will throw away more bits, but that's all. So we are starting to see that it is important to send a very long string of bits to be able to generate a long enough key, because from all of the pulses sent, most of them are going to be lost or discarded at some point. There is something else that could go wrong. It is that the polarization of some photons change in the flight from Alice to Bob. There are some media that affect the polarization of photons, called birefringent media, and they can rotate a bit the direction of polarization. For example, some optical fibers don't preserve polarization, and if you apply high pressure here and there, or change somehow the temperature non-uniformly, photons' polarization will be affected, and if Alice sent a vertical photon, there will be a probability that that photon is detected as horizontal. He would be detecting a wrong bit when, even without the presence of an eavesdropper. Of course, you can always get some expensive polarization preserving optical fiber. Or you can also encode your data bits, not in polarization, but in time of arrival of the photon to the detector, for example. You generate a time window and you split it into two. If the photon is sent in the first half, then it is a 1, and if it is sent in the second half, then it is a 0. There are some classical error correction algorithms that group some bits together and perform some parity checks. But this involves shifting even more the string data, reducing the length of the eventual key. If you have a string of m bits with an error probability epsilon, then the number of bits that you have to compare to correct for errors is given by the Shannon's noisy channel expression, where the larger epsilon is, the larger the number of bits you have to waste in this error correction process. Another important source of errors are dark counts. These happen when there is no photon arriving at the detectors, but the detector clicks. This could happen because of stray light getting into the detector or because of a photon is spontaneously created due to thermal noise. The rate of dark counts is something that is calibrated in single photon detectors and can be as low as a few tens of clicks per second, but it can never be zero. Imagine that Alice sends a photon that never reaches Bob detectors, but the wrong detector in Bob's sides does click. You can try to minimize this by synchronizing Alice and Bob so that Bob's detectors only read or accept those photons detected in a small time window when a photon from Alice is expected. All of this affects the length of the final private key that can be shared between Alice and Bob. Also, these phenomena are introducing errors to the data bits, but you can't know if the errors are due to your equipment or to an eavesdropper. You have to assume that is the latter, so you have to make a very good job in reducing your setup error, characterizing it. Otherwise, there is no room for additional error and the protocol won't guarantee you a secure key. May science be with you.